Now let's assume we want to check for a ratio or proportion. Now when would we do this? Well, we know that in news networks we always hear the 46% job approval of their senator or the president, or 56% approval. Well, this represents a ratio or proportion. So when we say 46% of the people approve of the job of their senator, the ratio is 46 over 54, which would be 46%. The point estimate for the target of the proportion is p hat, and the opposite is 1 minus p hat. So from above, our p hat is 0.46, and 1 minus p is 0.54. In order to calculate the confidence interval around this ratio, we're going to use an equation similar to the ones before. However, this time we're going to use a z multiple instead of t. Now, the standard error of p hat is given by the following formula. It's the square root of p hat times 1 minus p over n. And this describes the error around our point estimate for the success proportion. Now, why are we using the z value and not the t value, since we had been talking about the variance before for the confidence interval around the population mean, and we switched to a t value? Why are we switching back to a z value? Well, let's look at the formulas for the standard error again and understand why this is occurring. Before, we had a standard error of the x bar, which is the sample mean, as s, which is the sample standard deviation, over the square root of n. Because remember, this population standard deviation wasn't known. And so therefore, we had an estimate. So this introduces a degree of variability. But the standard error for our proportion, our p hat, doesn't have that extra variability. On the left side, we have the variability of the mean, estimating the population mean, but we also have the estimate of the standard deviation, estimating the population standard deviation. We don't have that on this side. We really only have our one estimate, which is the p hat. So because of that, we don't need to use the t distribution. We're going to be going back to the z distribution. But remember, as the number of observations get large, the t distribution tends to normal anyway. So as the larger and larger number of observations, you wouldn't see that much of a difference whether you use the t distribution, a t multiple, or a z multiple. On the right, we had a survey of 500 people based on the president's approval rating. In this case, it was found to be 55%, 275 approve, 225 disapprove. So our sample size is 500. So the sample proportion is going to be 0.55. Now, if we want the confidence interval, we're going to choose the p hat plus z multiple times the standard error for p hat. The z multiple is calculated with the norm.s.inv function. Again, this is the standardized norm function. We put in the area of the curve 0.975, and you might say, well, why is it 0.975 when we want a 95% confidence interval? And that's because, again, for this function, we're using the two tails. There's no 2t function. So what we have to do is we're basically going to say that we're looking for 2.5% on each side. So what we need to know is the 0.975, and this gives us 1.96 as a result. So further, we have the SE of p hat is equal to the square root of p hat times 1 minus p hat over n from our formula, which is 0.55 times 0.45 divided by 500, and this gives us 0.022. We plug these values back into the formula, and we end up with 0.55 plus or minus 1.96 from our z multiple, which equals 0.5064 for the lower bound and 0.59 for the upper bound. And we will interpret this as the president's approval rating was found to be 55%, and it could be as low as 50%, and it can be as high as 59%. So that's a key thing, because the margin of error is determined by the part of the equation after the plus or minus. It is the 1.96 times 0.022. So in this case, the answer for that is 0.0435, which we round to 4.4%. So we can say that our margin of error is 4.4%.